So the previous video talked about taking two resistors and combining them in series. Now I want to think about what happens when I take those same two resistors and combine them in parallel. So of course I know that when I combine circuit elements in parallel, that means that there's a junction. The current will come into that junction and then split. Some of it will go across element 1, the rest of it will go across element 2. That'll recombine at a second junction and then go out through the wire. So I know that whatever current travels across element 1 cannot also travel across element 2. The current come into the junction, split, go across my two elements, recombine, and go out of junction on the other side. So when I think about what's going on for resistors in parallel, let's start by applying the loop rule here. And so when I apply my loop rule, there's two loops that obviously make sense to apply. The first one is if I have a loop that goes across the battery, across resistor 1, and then comes back to where I start. So I'll start here in the bottom left corner, go across my battery from negative terminal to positive terminal, so that's a voltage increase. And then I go across my resistor in the direction of the current, so that's a voltage decrease. And so I know that since there's only those two elements, whatever I gain across the battery, I have to drop across resistor 1 for my loop rule to hold. Well, there's a second loop that I can go across. Again, start down here in the bottom corner. Whatever I pick up across the battery, here I have to drop across my second resistor, because again, there's only two elements in this loop. Well, obviously, if the voltage of the battery is equal to the voltage drop across R1, and it's also equal to the voltage drop across R2, it's pretty easy to see that that means that the voltages across resistors 1 and 2 have to be the same. So what this means is that when I have resistors in parallel, they have the same potential difference. So the voltage drop is the same across resistors in parallel. So we know that piece of information. Let's take advantage of it. So I can think about my circuit where I've got my two resistors combined in parallel. Of course, I can redraw this circuit to think of it again as now those two resistors are combined into a single equivalent resistor. And so let's think about the junction rule, use the junction rule with each of these circuits. So for the circuit on the left, where I still have my two resistors individually drawn out, if I apply the junction rule here, there is a junction up top. There's going to be the current coming into that junction from the battery. It's going to split. Some of it will go across resistor 1, the rest will go across resistor 2. So I end up with this equation here that tells me that the current coming out of the battery has just got to be equal to the sum of the current going across resistor 1 and the current going across resistor 2. I have another junction, but it gives me the same equation. All I've changed is what the current into the junction is versus what the current out is. But I still end up with the current that goes back into the battery here is equal to I1 plus I2. Well, what if I take my second circuit? So the circuit over here on the right that has my two resistors drawn as a single element with the equivalent resistance. Well, of course, there's not a junction in this circuit anymore. There's no node for that current to come into and split. So what this means is that the current coming out of the battery has to be the current that goes across the equivalent resistor. So I noticed I have two equations. Both of them are solved for the current coming out of the battery. That's the same in both cases. And so what that means is that the current across the equivalent resistor simply has to be equal to I1 plus I2. I can use Ohm's law again here, solve that for I get V over R, and so the current across my equivalent resistor is going to be V divided by the equivalent resistance. The current across resistor 1 is V divided by R1. The current across resistor 2 is V divided by R2. And of course, because the potentials are the same across all three of those resistors, V's cancel out, and I'm left with my expression that tells me how to calculate the equivalent resistance for two resistors in parallel. Notice I'm still summing, but I'm not summing the resistances themselves to get the equivalent resistance. Instead, I've got 1 over the equivalent resistance equals the sum of 1 over R1 plus 1 over R2. So a couple of details to keep in mind about this equation. One is it always works out that the equivalent resistance is less than the resistances of either of the resistors that you've used to build it if you combine them in parallel. The second thing I probably want to remember here is that this looks very similar to a rule we use to combine capacitors. It's just that 1 over C equivalent equals 1 over C1 plus 1 over C2 was how we combined capacitors in series. So again, that's an easy way to make a mistake, is to just end up grabbing the wrong rule because it looks very similar, but one of them's for capacitors in series, the other's for resistors in parallel. Now, the other mistake that's really easy to make is we go ahead and do this summation on the right and forget that that's not the equivalent resistance of the circuit, that's 1 over the equivalent resistance of the circuit. So if we only have two elements that we're combining in parallel, then it's probably useful, or at least it can be useful, to go ahead and write it out this way, which is an algebraically equivalent expression. All we've done is basically take the previous equation and solve it for the equivalent resistance, and so we're left with this expression, R1 times R2 over R1 plus R2. So if we're just combining two elements in parallel, this equation gives us a way to make that calculation for what their equivalent resistance is without having to worry about forgetting to again invert and solve for the equivalent resistance as opposed to 1 over the equivalent resistance.